Can you hear me online? So we were looking at implicit free list, how to build a dynamic memory allocator using implicit free list. And today we are going to complete our discussion of dynamic memory allocators. So I was telling you that some of the low order size bits are always 0 to ensure alignment. So if you have an 8-byte alignment, your address, your size are going to look like, they're going to be 3 bits. The 3 least significant bits are going to be always 0. So if you have 8, if you have 16, and so on. So we can sort of steal those bits from the size, and we can use them for a different purpose, because we know that those bits are always going to be 0. The thing is, when you write the allocator, you have to, when you're reading the size, you have to mask out those bits, and when you are using those bits, you have to do bit masking to set or reset those bits. So size bits, some of them are always 0. We are going to use 1 bit to specify if the block is allocated or free. And this is where we were. So an implicit free list is implicit because you keep the size of the block in a header. So there's a header word, the metadata, and there is a payload. And in order to find a free block, you traverse the entire list and using the size to advance to the next block. And the problem is that the allocation time, the time to find a free block is linear in the total number of blocks. So ideally, we should not have to traverse over the allocated blocks. We should only look at the free blocks to find the block that we want. And we will get to that in a minute. So there are different placement policies. The free list at this, if we take this as an example, if we want to allocate a block, if the user asks for a 4-byte block, then we have a number of options. So which one we pick is decided by our placement policy. First fit is the fastest. The first block that you find that has enough bytes to satisfy the user request, you just pick that block. Now, pretty fast, but not the best thing, because you end up with a lot of internal fragmentation. The block you find, the first time you find a block that fits the user requirement, it may have a lot of, it may be a very big block. So next fit is where you start the search where you left off in the previous time, you search for a block. And best fit is really what you want. Best fit is you keep reversing until you find the block that has the least number of bytes, but the block can still satisfy your request. So if you have a list with free blocks of sizes 4, 8, 12, and the user asks for 5, then this is not worth it. And between these two, you have a choice. In best fit, you will pick this one. And in these other fits, you might end up picking this one. If this is before, when you're traversing, if you encounter this before the block with 8 bytes. These are matters of policy. Once again, there's a distinction between policy and the mechanism for traversing the list. So mechanism is one thing, And the policy to place the block is another thing. And this distinction between mechanism and policy is very important in systems programming. And when we are building systems in general, we have to first come up with mechanisms to support the policies that we want to evaluate or try out. So with implicit free list, how do you allocate in a free block? So it's a little bit tricky because, so suppose I have a request for 4 bytes, and this is the block that I want to give to the user. This could be due to different reasons, either because I have a next fit policy or whatever reason. But look, this block has 6 bytes that in it that are free, but we only want 4 bytes. So what we can do is we can create a new block. Instead of giving the whole block to the user, we can create 2 blocks. One with 4 bytes, where we allocate, which we allocate for the user, and one with 2 bytes that is free. So this is called splitting, and splitting is relevant when you're allocating a block. When you're allocating a block, and if it is too big, then you don't want to just waste the leftover bytes. You can create a new block. So the code for that is here. So we have a pointer and we have the length that we are looking for, and we want to add a block to our list of allocated blocks. So this is pretty clever. The first thing we're doing here is we are, due to our alignment requirement, we are rounding up the size to an even number. So we first do a right shift to drop the 1 bit at the least significant bit. If it is 1, that bit is now dropped from our number, from size. And then we left shift by 1 to multiply it by 2. So we have the size with the same number of bits as before. So an example is, what is a good example? Let's say we have a number size. The user asked for something, and the new size is 11. So that's 11. That's an odd number, right? We don't want to allocate a block with an odd number. So we do this clever thing. We first do a right shift. So a right shift will make this number, and we then do a left shift. So that will make it this is some kind of overflow. Well, this is even, but it's less than 11. So maybe we need more bits, but you get the idea. What we are doing here is we are turning this size into an even number. So our old size is, we dereference the pointer and we mask out the allocated flag once again. So -2 in 2's complement, we saw in the last lecture, it's masking out the low order bit. And we get the old size. So now we are setting the size of the block that we are going to return to the user. And that is new size, and this is a bitwise OR. And this bitwise OR with 1 is going to set the allocate bit. And we are setting the new length of the block with this line. So when you are writing code for allocators and you do use the optimization where you steal the low order bit of the size header for a different purpose, you have to do these things. So this code is just to show you that you have to use bitwise OR, bitwise AND with a mask. You can create a mask this mask here, -2, 2's complement is 1, 1, 1, whatever the number is, 0. And this one is a mask that will, so when you do a bitwise OR, so 0 or 1 or 0 or 0 is always 1. Oh, sorry, with 1 is always 1. When you do an OR of any bit, 0 or 1, with 1, you get a 1. So this is the way to set the allocate flag. So you will have to do these clever tricks in, this is part of your, this optimization is part of your assignment. So what you're doing here is, if the new size is less than the old size, it means that what you have allocated for the user is less than the total size of the block before the request. In that case, what you're doing is you are creating a new block. Instead of throwing away those words, you are dereferencing P is the pointer, the start here, plus new size, whatever size that you have given to the user. You are setting it to the difference between the old size and the new size, which is 2. So basically, you're setting the header for this new block after splitting. So splitting is an allocation time and allocate time decision. When you find the best block that you want to use for the request, for the malloc request, you have to check if there are any words that you're wasting, and can you create a new block out of those leftover words. And here we are creating a new block out of that. So when I did this example here, this one, you need a bigger bit pattern because 16 does not fit in my four bits that I picked. So I'm not going to create a new example. I think you get the idea. We are dropping off the bit here, the least significant bit, just in case it's 1. If it is 0, we don't care. And then we are doing a left shift to multiply it by 2, because you saw what happened when I was doing the example. We end up with a smaller size than freeing a block. When we free a block, the simplest thing we can do is we can simply reset the allocate bit, allocate flag, the bit that tells us in the size header if this block is allocated or not. So once again, we can do this, just one statement in C, and this once again, this pattern, the 2's complement representation of -2, the least significant bit is 0. So doing an AND of any bit with 0 is a 0. 0 and 0 is 0, 0 and 1 is 0. So this is a pretty clever way to reset the allocate bit. Now this block is free. So in our implicit free list, if we do this to a block, when we are traversing, we can actually read the bit and we know that this block is not allocated. But this has a problem. We can end up with false fragmentation. So this is an example here. This is our state of our heap. And so we have this block here in green with 4 words, and then we have a block that is free with 2 words. And so what we do is we say that we want to free this this green block. Okay, so we will end up with this. We have a block. We have 2 contiguous next to each other. We have 2 contiguous blocks that are not really merged together. So one of them has 4 words and one of them have 2 words. We could merge them to prevent false fragmentation. If the user says, give me a block of 5 words, we have enough contiguous words or bytes to satisfy the request, but we just don't have the appropriate bookkeeping to tell the allocator or to tell us that we do have this space. We are traversing, we see a block of 4 words and we say, let's go to the next one. 2 words, oh my God, we don't have a block. But really, we do have it. So this is the motivation for coalescing. When we free a block, when we allocate a block, we do splitting. When we free a block, we do coalescing. We merge, we check our neighbors. We check our neighbors and we do coalescing if our neighbors are also free. So there's enough free space, but the allocator won't be able to find it. Okay, so how do we do coalescing? Well, we know where the next block begins because we have the size of the next block. So we jump to the next block by adding the size of the current block, and this is our next. And when we dereference next, when we read the size of next, we mask out we read the allocated flag. And if that is 0, it means that the next block is free. So this is pretty clever. We add the size to our pointer to go to the next block, and we do this AND operation with 1. And we know that if the result is 0, this next block is free. It's not allocated. If the result was not 0, we know that our right neighbor is allocated. We can just go home. We don't have to bother with anything. But since our right allocator is not allocated, we can just set our size to include the size of the next block. So dereference the size header of current block and add the size of the next block to make it one big block, right? So make it one big block. This 2 can be there, but who cares? It's logically gone. When we traverse the list, we will see 6 and we will go to the next block 6 words away. We will not care about whatever 2 was there before. Okay, so this is called coalescing. What do we do with the blocks to the left? So the blocks to the right are easy because I can just look at the size and I can jump to the next block to peek into the size of the next block. But what about if there's a block that is free? What if I'm freeing this and there is a block free to the left of it? Okay, so for this, we use a trick called boundary tags. So we replicate the size and the allocated word or header at the bottom of the free blocks. So it logically allows us to traverse the list backwards, but it requires extra space. And this is how it looks. So we have the header already here with the allocated flag, and this is our payload and everything. And what we do is we add a footer to the end of the block. And this footer is a replication of the header. So, and this contains the size. So what happens is now, if we have the header, the payload, and the footer, and then there's a block next to it, which has the header, payload, and the footer. And if I'm pointing here, then I know that my footer is, the footer of my left neighbor is 1 word away. So I can read the footer of my left neighbor and I can figure out the size of the left block. So this is a clever technique invented by Nuth in 73. The downside is we are going to need an extra word. And if we have a lot of small blocks, then this is a pretty high overhead. But it's worth it. Now we can coalesce in both directions. We know that the size of the left neighbor is just 1 word away. It's a invariant. It's always true because we always add the footer to the block. So now our blocks look like this. So this is called boundary tag, a boundary tag to help the next block with coalescing. Let's see some examples of what we can do with boundary tags. So here's a number of cases, and we want to free. So this is our boundary tag. This is our boundary tag. This is the footer. This is the header. So similarly, these are allocated. The green ones are allocated, and we are freeing the yellow one. Well, in this case, there's no point. We cannot coalesce the block that we are freeing with either the left neighbor or the right neighbor. So we have to live with it. You cannot always coalesce. It depends on the pattern of requests up to that point, what blocks have been freed and all that. Case number 2 is where we are freeing this block and there is a block next to it, to the right of it, that is also free. So what we can do is we can coalesce these two blocks, and we can add n plus m2, and we can just make it one big block. And then we need, so this is our one big block. This is the header of our new coalesced. Coalesced is sometimes a strange word. It's really merged, right? Easy. Coalescing is more fancy. Computer science is all about making fancy terms and all. And there is a footer here, n plus m2. So n plus m2, n plus m2. So we coalesce these two blocks and we add the header and the footer. Note that the allocate flags in both the header and the footer are now 0. What if we have a block, we are freeing this block over here, but we have a block to the right, to the left of it that is free, okay? So now with boundary tags, we can simply check the allocate bit here. If we have a pointer to this block, when you write code, you will know that you will have a pointer to a specific block, and you can just subtract -1 and do your bit masking and everything to read the proper size of your left neighbor. And now I can coalesce in the other direction. So now my new block, this merge block, has a size of n plus m1, and the allocate flag is 0. And I have a much bigger block that is. So I am freeing the block, and I can check in both directions. I can check both my right neighbor and my left neighbor. So in this case, what is the size of the new block? N plus this plus this. So I can coalesce in both directions. I'm freeing the yellow block, and I see that to my left, the block is free. To my right, the block is free. So I'm just going to create a one big coalesced block, and I'm going to add the sizes of all the blocks together. I'm going to have a header, and I'm going to have a footer, and I'm going to set the allocate flags to 0. All right, pretty simple. And you will just write this code in like a few minutes. This is okay. Internal fragmentation with boundary tags. Once again, now we have 2 words dedicated to metadata, header and footer. And so my payload, the actual data the user wants to put in the block, is now we have more internal fragmentation. This is an example of internal fragmentation. When you have to allocate a block that is bigger than what the user requested, and you can do some tricks to optimize this. You can actually, we don't need the footer when the block is allocated. We only need it when it is free. So we can do some clever tricks to steal some of the bits from the footer when the block is allocated. It's a bit more work. Sometimes it's worth it. Sometimes it's a lot of overhead. Placement policies. So key allocator policies, first fit, next fit, best fit. Okay, you can think about this, but you don't have to do this optimization in this assignment. But think about if you can reuse, repurpose, it's a good, can you repurpose some bits from footer when it is allocated or when it is free? When do you really need the footer? So it's a good thought experiment. We'll explore this in the homework. There is a trade-off between throughput and fragmentation. So best fit really, as I was saying in the last lecture, when you put so much effort into finding the perfect fit, it takes time. It takes CPU cycles to do that. So throughput and fragmentation, there's a trade-off. There's a space-time trade-off. So we will look at a technique which will approximate best fit placement policy without requiring such segregated free lists. And that is also part of your assignment. Splitting policy, when do we split free blocks? When we allocate them and the block is too big compared to the user request. How much internal fragmentation are we willing to tolerate? These are all policy decisions. You can build an allocator and then do some benchmarking, run some real-world applications or the benchmarks we have given you, and find out for yourself that, oh my God, I'm spending too much time when allocating a block. malloc, allocation, free, these things are on the critical path. Applications don't want to wait for these things. Applications want to spend their time and resources on what the user actually cares about. We can coalesce right away on every free, or we can have a more elaborate policy. We can defer coalescing. We can say that, look, on every free, I don't want to coalesce. I don't want to give users the illusion that, sorry, not the illusion, I don't want to waste time coalescing on every free. So you can coalesce every 10 free calls to free, or you can have an internal metric. You know, when my fragmentation reaches, I don't know, 60%, whatever 60% means, I'm going to start coalescing. Coalescing when the amount of external fragmentation reaches some threshold. So once again, these policies are a matter of fine-tuning. And once you have the base mechanisms in place, once you have code to do for these 4 cases, it's up to you. You can evaluate lots of heuristics, lots of different policies. So implicit free list, the problem is that the worst case cost is linear in the number of allocated and free blocks. So free cost, constant time, even with coalescing, because we use boundary tags, we don't have to traverse to find blocks that are free to the left or right. And it's not really used in practice because of the allocation time or this problem, where we have to traverse all the blocks. But the concepts that we have learned, boundary tags, splitting, coalescing, are applicable to all allocators. So next, we're going to look at explicit free list. So explicit free list, an allocated block looks the same as before. But a free block has explicit next and free pointers. So when we add actual pointers, next and free, to our blocks, we are no longer using the size of the header to go to the next block. In the implicit free list, we were indirectly using the size of the block to traverse free blocks. And that's why we had this problem that the search time was linear in the total number of blocks and not the total number of free blocks. So now by connecting the free blocks together using explicit next and free pointers, we are going to solve this problem. Now, when we will traverse every time there's a request to allocate a block, we will traverse only the free blocks because all the free blocks are connected by the next and free pointers. It's the linked list. In fact, it's a doubly linked list. So the cool thing is that the next free block could be anywhere. They are not necessarily next to each other. As we allocate on free blocks and we fix the next and free pointers, next and previous pointers, our actual free list in memory could look very messy. We still need boundary tags, and we only track free blocks, so we can use the payload area for the whole the actual data. So logically, when we draw on slides or paper, we show this very neat diagram with next and free. But in reality, depending on how we whenever we free a block, how we insert the block in the free list, our free list might look very messy. There might be a block, the next block may be here, and the previous one here, and then the next one somewhere else, and this is how free lists look like. Depends where you, when you free a block, where do you add that block? Okay, let's do some examples. And these are conceptual graphics where the arrows point to the start of the header, to the end of the header, to the, that is not relevant. These are just figures. So initially, the blocks are connected like this. So this is a start of the heap, and then there is a free block. This is a free block. This is a free block, next, and then these are the previous pointers. And we want to allocate a block here for the user. So now this is allocated. So we want to fix this pointer. We want to split the block into two, and we will adjust this pointer to point to this free block, and then adjust this one to point to the next one, and adjust the previous pointers, and my new state of the heap now looks like this. So because this is allocated, so these are gone now. These pointers are gone. This goes here, this goes to the next one, and then to the previous one, and the previous one. All right. So this is how an explicit free list looks like. Now, when you are going to traverse this free list for, if there's a new request, you're going to ignore this. So this is the beauty, this is the benefit, sorry, of explicit free list. You are no longer traversing every single block in the free list, allocated or no. You're no longer traversing every single block in your heap. You're only traversing the free blocks because you're explicitly maintaining, storing pointers, next and previous pointers to remember, to connect all the free blocks in a linked list or a chain. Okay, but now we need an insertion policy. Now we need an insertion policy. When we free a block, in implicit free list, it was pretty simple. Everything stays where it is, and you just use the sizes to split or coalesce blocks. But now we need to know where can we insert a block, a newly freed block. So last in, first out is a policy that is last in, first out. Whenever you free a block, you insert it at the head of the free list or the root of the free list. You insert the free block always at the start of the free list, at the beginning of the free list. So insert the free block at the beginning of the free list, and the last block you insert will be the first one you grab for allocation. So imagine we have, I don't know, this is my head of the linked list. These are my free blocks. Okay. And I free a block A. Okay. So my new list with the LIFO policy is going to look like, So the head, so I'm going to insert the newly freed block A to the beginning of the list, and everything else is as before. But look, when there is a malloc request now, and if A can fulfill the request, I'm going to use this to satisfy the malloc request. I'm going to use A. So A was the last one to enter the free list, and it's the first one to go out. Last in, first out. The other policy is the address ordered policy. And studies suggest that fragmentation is worse than address ordered. And as I was saying, that memory allocators are full of heuristics. You cannot sometimes reason about why something leads to less fragmentation. So the second one is address ordered policy, where all the blocks are in an increasing are in address order. So the address of the previous block, the address of the current block is less than the address of the next one and greater than the address of the previous one. So we maintain the free list in such a way that the addresses of the free blocks are in an increasing order. And studies suggest that fragmentation is lower, but really what we are trying to exploit here is locality. So if in virtual memory things are next to each other, then the expectation is that in physical memory, they will also be next to each other. And this is because the page size is typically 4 kilobyte or something. So the address ordered policy, we are not going to look into it in detail, but it is trying to exploit locality by keeping things in an increasing order, in a specific order with respect to addresses. Whenever you do something like this, you're trying to exploit cache locality, TLB locality, memory locality. Locality is everywhere. We have seen many examples of caches in the memory hierarchy, and this locality is targeted by high-level software. And when we write memory allocators, of course, we are trying to exploit locality. So here's an example. Now let's do freeing. So whenever we free, remember, we need to consider coalescing. So with explicit free lists, now we need to consider coalescing as well. So suppose we are freeing this block in the middle here, and the blocks to the left and right are allocated. So this is pretty simple. We insert this newly freed block. So this is the block we free. And what we are going to do, we are going to insert it at the root of our linked list or free list. So this is the last one. So we're going to insert it at the root of the list, and then we're going to adjust this pointer, because the next one is now, root was previously going here, but since the root is now going here, we know that the next one is the one where the root was pointing before. And then we're going to adjust the previous pointer. And so now this is the last one to enter the free list, and this will be the first one to leave the free list if we allocate this block. Okay, so what about this case? So now we have a situation where we have some free words at the right of the block, and we are freeing this block over here. Okay. So we're going to splice the successor block. We are going to coalesce both memory blocks and insert the new block at the root of the list. Okay, so what we're going to do is we're going to do all of this is, so this is going to come here, and then this will go here, this will go here, and this will probably go here. So let's see. Right, so my root is now here. This is the whole thing that I'm freeing. So now I'm coalescing. I still have the boundary tags. In an explicit free list, I still have the boundary tags. So I can figure out my left and right neighbors in both directions, if they are free or not. So I create this large block. All these pointers are gone because this is now one big block. I adjust these pointers, and now this block points to where the root was pointing before. Okay. So now I have a different situation to the left. I don't know what I was saying, right or left, but I understand. I hope you know more than me what is right to a block or what is left to the block. So here we have a block that is free, that is to the left of the block that we want to flip. Okay. So we're going to create this one block. This is going to point here. This is going to point to the next one. And so we're going to have this situation. So we're going to keep changing our next and previous pointers the same way we do in an ordinary doubly linked list. Okay. So now I'm freeing a block, and I have a free block to the left and one to the right. Okay. So I'm going to create this one huge block. I'm going to coalesce in both directions, and then my root is going to point here, the next one is this, and the previous one is this, and then all these other pointers. These diagrams are logical. I'm not showing all the connections across the heap. Okay, so last in, first out policy is pretty simple to implement. Whenever you free a block, you adjust the next and previous pointers to insert the block at the beginning of the free list. In this figure?
Yes, in the block we want to free, the left block we want to free, doesn't point into the right block.
No, we want to free this block. We want to free this.
Yes, I mean the block.
And this is free, and this is free.
Why doesn't it point to the right block?
Oh, you mean why is this?
Yeah.
This is just a figure. Like, this is how the heap looks like at some point in time. So they are all connected in a. So this is connecting here. This is probably connecting here, but I'm not showing everything, right? This is what I'm saying. I'm only showing the parts that are relevant to. They can point anywhere. It doesn't matter. So you could start with, you could make a figure where you have this, and then this, and then you try to coalesce again. So compared to implicit list, so this is your task in the assignment as well. You have to make an explicit list, and in lab 5 and lab 6, we taught you how to make an implicit list. So now you have to transition to an explicit list. So compared to an implicit list, the allocate time is linear in the number of free blocks instead of all blocks, much faster when most of the memory is full. So you have a few free blocks and you only need to traverse a few blocks. Okay, this is another trade-off. If most of your memory is free, the difference between implicit and explicit free list may be less obvious. So slightly more complicated allocate and free, since we need to splice blocks in and out of the list, and we need to set these pointers next and previous. Is there internal fragmentation due to next and previous pointers? Not really, because when we allocate the blocks, we don't need the next and previous pointers, okay? So this is an important optimization we asked you to do. Remember that when you create an explicit free list, the block structure, either the block structure or the pointer that you return to the user of the malloc package should not consider next and previous pointers when the block is allocated. When the blocks is allocated, you don't care, you don't traverse allocated blocks, you only traverse free blocks. So you can reuse the next and previous pointers when the block is allocated for payload. You don't have to waste two words just for okay, typically it's always it's used with a segregated free list, which we're going to look next. So segregated free list, we have multiple. Segregated means we are segregating the lists based on size. So in memory allocators, in the design of allocators, segregation is an important idea. Sometimes we segregate blocks or objects or data based on size because it is more efficient to manage different size classes separately. Sometimes we segregate blocks or objects based on their lifetime, how long a specific block lives. Lifetime means if you have program execution time of 1 hour, some variables will no longer be alive or used after half an hour, and some will have a very long lifetime. So lifetime is about how long an object or a block survives. We can segregate things based on lifetime as well. This was a, okay, let's focus on this. So this is segregation based on size. Okay, so we have multiple free lists, multiple explicit free lists, and we dedicate each list to a specific size class. So this list has all the blocks of sizes 1 or 2. This list has all the blocks of size 3. This list has all the blocks size 4, 5, 8. And then at some point, we decide to have a single free list that could have a variable number of variable size blocks, because we cannot have an infinite number of free lists. The good thing about this is if the user says, give me a block malloc 4, we go exactly to the size class, and our search is much faster than searching all the free blocks in the entire heap. We will only search one free list. And if there is a free block in that list, we can literally just grab that free block. Just go to the free list for that specific size class and grab the first free block that is available. Okay. So typically you have a separate class for each small size. For each small size. And for the larger sizes, you have one class for each power of 2. So at some point, you increment your sizes in power of 2 or in some other way. In the assignment spec, we are telling you how to do that. And picking these size classes and everything is a matter of experience. It's a matter of empirical evaluation. It depends on your specific application. Some applications create very large objects, arrays, data structures. Some applications create a lot of small variables, objects. It all depends on a number of factors, how you pick your sizes. So given an array of free lists, each one of some size class, to allocate a block of size n, we need to search the appropriate free list for a block of size m is greater than n. So m in here means metadata. You need, if the user says, give me a block of size n, you need to add the previous, next, all those headers and everything, all the metadata, and you need to search the appropriate class for that request. If an appropriate block is found, we split the block and place the fragment on the appropriate list. And this optimization is optional. So when you grab a block from a specific free list that belongs to a specific size class, you may end up with a block after splitting that is appropriate for a different free list of a different size class. Okay. So this way you can have your free blocks in the appropriate free lists. If no block is found, then we try the next larger class and we repeat until the block is found. If no block is found, we request additional memory from the operating system. S-break is deprecated. I was going to change that. We use mmap today. In the kernel recently, they don't support S-break anymore. So then you go back to your mmap allocator you have written, or the mmap system call that we told you how to use, and you grab more memory from the operating system. And then you allocate the blocks in this new memory and place the remainder single free block in the largest size class. So when you get memory from the operating system, initially you place the memory in the largest size class. Because when you do mmap, you typically grab a big chunk of memory, 4 megabyte in your assignment. And then you create smaller chunks to keep placing in the appropriate free list. So to free a block, we coalesce and we place on the appropriate list. High throughput, log time, not linear, for power of 2 size classes. Better memory utilization. Here's the interesting thing. First fit search of segregated free list approximates a best fit search of the entire heap. So in the extreme case, if you have a size class for every possible request in the world, which is not possible really, I mean, in computer science, nothing like, but just do a thought experiment that if you have one free list for every single size class, that is a best fit policy, right? This is the best fit policy. Now we try to approximate that, but we cannot really achieve 100% best fit. And segregated free list takes us very close to best fit policy. Okay, so there is this book, which I have it on my shelf, but I never really read it. It comes in many volumes, and it's for decoration, really. But if one of you wants to read, there's a lot of information in that book. And then there is this seminal paper. If for your assignment, you figure that we need more information, then you can read these papers. Garbage collection. So that's it for your assignment. This is all that you need to know for your assignment, and wish you good luck. We have some time, so we can look at garbage collection. Implicit memory management, as I was telling you the other day. So here we have a situation, automatic reclamation of heap allocated storage. So the free path is gone. The programmer is no longer responsible for freeing memory, and this is a huge burden taken off the shoulders of the programmer. And that's why these languages here are really popular, especially Java. And these are called managed languages. Managed languages. Because they manage memory on behalf of among other things, they manage memory on behalf of the programmer. And we call C and C++ native languages because they are very close to the actual memory system, and the programmer is managing it themselves. The other reason is that Java actually uses a virtual machine, but we want to get into that. And that's why we call it managed, and we call C and C++ native. These languages run on top of a very elaborate and sophisticated runtime. They don't interact directly with the operating system. There's an intermediate layer, a runtime environment. You might have heard of the Java virtual machine, JVM. That's what I'm talking about. So if you have a situation like this, if you have a method foo, and the programmer grabs a block of free memory for something, and then there's a return. So this P is now garbage, okay? So if you write this code in C, you have a problem. The problem is that you allocated something, but you never freed, and this is a memory leak. And if this function runs over and over and over, you will end up with a lot of allocated memory on the heap, but there is no one to collect it. Unless the programmer calls free, the allocator doesn't know what to do. And garbage collection solves this problem. If you have a garbage collector, it will automatically figure out that once this function returns, P is no longer needed. The scope of P ends after this function returns. So P cannot be used outside this function anymore. And the garbage collector will figure out, hey, P is not reachable. Okay? Reachability, reachable. When you write functions and the function returns, anything you declared inside the function cannot be referenced from outside the function, right? Unless you have a global variable or something. So this is the kind of analysis the garbage collector does to figure out all the pointers that are no longer reachable. So I will tell you why in C, you cannot have precise garbage collectors. In Java, Perl, ML, you have precise garbage collectors because the language has support for distinguishing pointers from other data types. In C, and pointer just looks like an integer. So the garbage collector has a very hard time figuring out if a specific word represents a integer or a pointer. Is it an address or is it an integer in use by the programmer? And so these languages, they provide a lot of sophisticated runtime support, and they limit what you can do with a pointer. If you have written Java code, you know that you cannot use your pointer to reference anything anywhere in the heap. You have to be very disciplined and careful with creating objects and with referencing the fields of the objects. You can't just add plus something to a pointer and go somewhere in the middle of the heap. But in C, you can do that. You can do anything with a pointer. And so the garbage collector has a really hard time figuring out, look, what is it? Is it an integer? Is it a pointer? Is it an address? What is it? So we call the garbage collectors for C and C++ conservative. They have to be very conservative. They have to be very careful. Anytime they see an integer that looks like a pointer, they just assume this must be a pointer. So let me not free the block. Okay. We're jumping a bit ahead of ourselves. How does the memory manager know when memory can be freed? Okay, this is an important question. How does an automatic memory manager or a garbage collector know? Automatic memory manager or garbage collector, same thing. How does it know when to free memory? If you free memory, if you make a mistake, it's a huge problem for the programmer, for the user. So garbage collectors have to be really careful. We can tell that certain blocks cannot be used. We can say with 100% certainty that this block here, P, can never be used again. It's not reachable. Once the function returns, P cannot be referenced from outside the function because it's declared inside the function. Okay, so this is the kind of analysis that can tell us that with 100% certainty that a specific block or a specific variable is no longer alive, dead, not reachable. So really, ideally, what we want from a language when we write garbage collectors is the memory manager can easily distinguish between pointers and non-pointers. And C makes it really, really hard. In C, you can do this. Okay, so now the garbage collector is looking at P and saying, oh, that's a pointer, that's an address. And then it's looking at I, the integer, and it's saying, well, that's an address too, right? This is a problem. In Java, you cannot do that. And in other languages, there is a very clear distinction between pointers and non-pointers. There are tags, there is a runtime type information attached to words to specify that this is an address, this is a pointer. In C, you can do this casting, and now I and P both look like pointers. A word in memory that contains P and a word in memory that contains I, they both look like addresses. So the garbage collector has to be conservative and assume that I is also an address of a block. Anyway, All pointers point to the start of the block. That's true in Java, but not in C. In C, you can grab a pointer and you can point anywhere in the middle of the block, and that makes it very hard for the garbage collector to. And you cannot hide pointers. What I just did was I was hiding a pointer inside an integer variable. The integer variable was masquerading as a pointer, right? We're going to quickly look at mark and sweep collection, which is the most popular, but there's a bunch of other that are used in Java. And the book, Johns and Lane Garbage Collection, is a famous book for if you want to learn more. All right, so the idea is that you have a bunch of nodes. Each block is like a node in a graph, and you have something called root nodes. And each block is a node in the graph. Each pointer is an edge. Each of these pointers is a directed edge. So now these are our blocks. These nodes represent our blocks. So we have locations not in the heap that contain pointers into the heap are called root nodes. So these are locations that are not in the heap, but they contain pointers inside the heap. What could that be? What can those root nodes be? Right, or it says right here, registers, content of registers, location on the stack, global variables, right? So this is an example. So this is a runtime stack, right? This is a stack. This function foo has a stack, and somewhere there's a stack pointer and somewhere on the stack we have p, right? But the actual block is inside the heap. The actual block is inside the heap, right? But there's a pointer to that block from outside the heap, coming from the stack of this function. So the contents of the stack, registers, global variables. Remember, there was an area in virtual address space for initialized and uninitialized data. That is global variables. So we take all these pointers, nodes, we call them nodes, and we call them root nodes. And then we do a reachability analysis. Then the garbage collector does a reachability analysis. So if I have a pointer from this node inside the heap, and let's say this is a struct with two pointers. This is a struct car, and then this is a pointer to registration number, and this is a pointer to whatever type, right? And so the garbage collector can see those pointers and make a note that, okay, these two nodes are also connected, reachable from the root node. So this is reachable from the root node, this is reachable from the root node, this is reachable from the root node, but there are some nodes that are not reachable from the root node. So after the garbage collector has done all the analysis, it knows that which nodes can be freed, which nodes are no longer useful. And so here, these nodes can be freed safely, and all these nodes have a pointer somewhere, right? And so things become unreachable when programmers write code. They change the pointers, right? Right. So what I was doing in the previous slide was exactly that. I was saving the pointer in I. I could say p equals null, and then after the garbage collector frees the block, I can come back and say recover p. P equals I again. I can redo my casting. That's why there is no garbage collector in C, and that's why you need sophisticated runtime to prevent this kind of behavior. In C, this kind of behavior is not illegal, and that's why the garbage collectors are really difficult. So we have a graph of nodes, and we do a reachability analysis. We follow pointers starting from the root nodes, and at the end, we know that anything we have not encountered is no longer used by the programmer. So these are dead nodes, and these are nodes that are living or alive or so non-reachable nodes are garbage, and reachable nodes are if there's a pointer to a node originating from the root node, then that node has is alive. So mark sweep, we use an extra mark bit in the header of each block. So just like the allocated bit, we now use a mark bit. So there are two phases. It's a two-phase algorithm. So now we're talking about mark sweep collector. We can build this on top of malloc. Once again, I'm saying it again, when you build a garbage collector for C, you have a conservative garbage collector. You are not going to be precise, as the student was just saying. So we have a mark bit in addition to the allocate flag. And in the mark phase, we are going to start at roots and set mark bit on each reachable block. And in the sweep phase, we are going to scan all the blocks and free blocks that are not marked. Okay. So here's an example of marking phase. So here's a root object coming from the stack or from somewhere. And there's a pointer to this block. Then there's a pointer to this block. So this one is alive. This one is alive. And then there's a pointer to this one. So we are going to mark all of these blocks. So after marking, after the mark phase, starting from the root object, so this is now marked. This pink bit is marked. This is marked, and this is marked. And so anything that is not in the graph, we haven't marked that. There is no marking bit set for that specific block. So what we are going to do is we are going to scan the heap from left to right, and we are going to see that, okay, there is a mark here. So this is allocated. Okay, there is no mark here, so I can free that. This is allocated. This is free. This is free. Okay. Sorry, this is allocated. This is free. So this is now after the sweep phase. In marking, I mark all the live objects, all the live blocks, starting from the root nodes, right? And in the sweep phase, whichever block does not have the mark bit set, I know that this is not part of the heap. Okay, programmer has given up the use of this block. So assumptions for a simple implementation, because we have to be disciplined a little bit, we need some discipline from the programmer in their use of the pointers. We have a new function that returns a pointer to the new block. Then we can read any field in the block using the read function, and then we can write any value at any specific location in the block, and we can get the header by doing a simple pointer arithmetic. Assuming that we have a function, magical function called isPointerP, that can tell us with certainty that this pointer is indeed a pointer to an allocated block. It's a really hard problem to write this function. It's a really hard problem to write this function in C, because everything looks like an address. Everything looks like an address. You look at a word, it has an integer in it. We don't know if it's an address or an integer. There are ways around this problem. We are not going to cover them here. Imagine we have this method isPointerP. We can have our marking phase implemented with this function. If it's not a pointer, just return. If the mark bit is already set, return. So if we are here, we know that the mark bit is not set. So we set the mark bit. If we encounter a block, we know that we need to set the mark bit. And then we are going to scan the entire block, each word inside the block. So this for loop is going to scan the entire block for pointers. It's going to check if this is a pointer. So recursively, we mark all the blocks that this block would point to. So this is a recursive operation. So this is how you are traversing the nodes everywhere. You are doing a depth first traversal. So once again, these pointers come from if you have a struct and then you have a pointer inside, and then you have a other pointer inside, and programmers create data types, structures. So this could be a block that has a lot of structs, and then you are following these pointers, and this may point to another struct or an array which is full of pointers. So then you're following those pointers. So this is what you're doing. And in the sweep phase, until you reach the end of the heap, if the mark bit is set, you clear the mark bit for the next phase of garbage collection. And if the mark bit is not set, if the allocate bit is set, you know that you can free the pointer. Okay, so a matter of policy is that you can do garbage collection when you're trying to allocate something and you run out of space. This is one policy. This may be a bad policy. You might want to do garbage collection somewhere in the middle when your heap is some % full, right? So this is once again a matter of policy. So this is a simple mark sweep collector. For C, the problem is that is pointer is really, whether or not something is a pointer is really hard to figure out. And in C, it's hard because a pointer can point to the middle of the block, and then so the header, like the garbage collector, doesn't know what is this pointer. And there are sophisticated data structures to track addresses of all allocated blocks, but we end up being conservative in our approach for garbage collectors that are for C or C++. These are not precise garbage collectors. Precise garbage collection needs runtime support from the language. Java was written from the very start to support automatic memory management, garbage collection. It's a managed language. So there is runtime support to distinguish pointers from integers. Ints looks like pointers. So if once again, if the programmer does something like store the pointer of Q in P and then saves it for later use, set P to null. Now P is no longer used. The garbage collector is going to probably going to free P, but at the same time, the garbage collector is going to scan, at some point scan I, the variable, and it has no idea what the programmer is trying to do. Why would the programmer store a pointer address inside I? It's going to assume the programmer it's just an address, or so this is the difficulty here. And the programmer can have not do this, cannot do this, but at some point say, hey, let me, whatever I save, let me grab this and start using it again. So now we have a bigger problem. The garbage collector has freed the block P, but the programmer is saying, let me revive that block and do something, right? So C is special. So state-of-the-art garbage collectors in Java exploit the generational hypothesis. The reason Java is popular and its garbage collectors, despite having some overhead, are still popular. It's a popular language because the garbage collector exploits the generational hypothesis, which states that most objects die young. So the infant mortality is very high. The way programmers write programs, and this is true, this has been observed over many, many decades, most of the objects the programmers create die really young, very quickly. What this means is that the garbage collector can, with very little effort, reclaim large portions of the heap, right? So if most objects die young, then you are only traversing the reachable objects. Remember that graph? You're only traversing the reachable objects in that graph. You're starting from the root nodes and you are only traversing the green ones, not the red ones. If that's the case and most objects die young, it means that whenever garbage collector wants to free up space, it only has to traverse a very small number of objects because most objects die young. And this is because Java is a very object-oriented language designed from first principles. It gives programmers, it encourages programmers to create objects. And so programmers create objects for everything. But most of them die young and few of them survive a very long time. So in Java, the collectors for Java, the heap is actually divided into two parts. There's a nursery for young objects, and there's an old space for mature objects. So this is how the heap looks like. In Java uses this terminology. So there's a garbage collector, and now there is a mutator. And the mutator is what the application code, the application. Just like we have a distinction between the application code and the kernel code for native language runtime, C and C++, Java makes a distinction between the garbage collector and the application, but they use a fancy name. I keep telling you, fancy words, fancy terms. Mutator, mutate, something that mutates the heap. That mutate means change, right? Something that updates the heap, and garbage collector, something that cleans up the heap, the sweeper guy. So the mutator allocates in the nursery, okay? In the young space, every object begins their life in the nursery, okay? And when the nursery is full, the garbage collector copies the reachable objects to the mature space. This is segregation, not on the basis of size, as was the case in the segregated free list. This is segregation based on lifetime. This is segregation based on the life of an object. So we are segregating objects. Young objects go here. Old objects go here. There is still a size segregation. There is a special space for large objects, and it's managed a bit differently. This segregation is to exploit the specific behavior and properties of each type of objects. And we can do things efficiently, exploit locality, and those things if we segregate things. If we mix, now this is not true in real life. In real life, you mix people up, but when you're building garbage collectors, you segregate people. You stay in your own rooms, please. So we have a different allocation policy for this space. We have a different allocation policy for this space. The trade-offs are different. Mature space is really very, very large. This is what we infrequently, rarely garbage collect. We don't garbage collect the mature space very often. And the intuition is that if something has survived the initial period of their lifetime, then they are likely to survive. They are likely to live a very long life, right? If the infant mortality is high, it means anything that survives is likely to have a very long life. So let's not let them live. Let them not look at their lives. Let them live in this very large space. And when we run out of it, we will garbage collect it. But let's focus our attention on the children, on the young objects, on the nursery, because there's a lot of room here. With a little effort, we can free up tremendous amount of space because those guys die very, very young, okay? None of this is applicable in real life, okay? Okay, so small effort, we can reclaim a lot of space, copy the survivors to the mature space. We are exploiting locality. We are putting the survivors next to each other. So these are survivors. And the survival rate is low. Very few survive the initial difficulties of life. So start allocating objects in the nursery again. When you copied everything out, you start allocating objects in the nursery again. Use different allocators for small and large objects. Nursery is typically copying. Copying nursery means that I'm copying objects out to the mature space. And mature space uses more sophisticated algorithms. Mature space is many tens of gigabytes, and we need to do something special for that. Nursery is something we try to fit in the our CPU caches. So we look at the size of a CPU cache, and we have typically 4 megabyte or so, or 16 megabyte nursery. So what I want you to take away from this is in the future, if you look at this area, segregation is an important concept. Segregation, size, type, you can segregate integers, all the integers go here, all the floats go here, and you can segregate things, objects on the basis of their lifetime, right? Typically, you have a nursery where you copy things out into a different space. You can actually leave them there and have an allocator that finds free space without copying. Copying means you actually copy the survivors to a different place, so the whole contiguous chunk is available for reuse, starting from the beginning to the end. Okay, so we want you to be careful when you write C programs. This is something for your revision, so you understand pointers. Honestly, if you're a gladiator and you want to understand what is the meaning of this, I'd be very happy, but this comes with experience. This is really crazy. Yeah, C is sometimes. All right, very quickly, 5 minutes. We're going to figure out all the bugs that could occur when programmers write use pointers. So the problem here is the scanf expects a pointer and address, but the programmer here is providing the value. And this pointer could point anywhere. This is an example of dereferencing a bad pointer. Internally, scanf is going to consider that this represents an address, and God knows what will happen. Assuming that heap data is initialized to 0, malloc does not initialize heap data to 0, calloc does that. So here the programmer is assuming that y, the contents of y have been initialized to 0, and then trying to use wait a second. Okay, get stuck. So what is the programmer trying to do here? Oh my God. Open the gates. No, don't do it. I was thinking of it. So here, what is X? I think this should be Y. Oh, so assuming that X is initialized. Oh, sorry, it's very easy. So here, you're saying yi plus equals, assuming that yi contains 0 and you're adding something, but yi could contain anything. So you have to be careful whether your memory is zeroed or no. Here you're allocating a wrong sized object. So you have a you're trying to create a 2-dimensional array. So you're first trying to allocate a number of pointers, and then you're trying to create a row of a specific number of ints. But what you have allocated here is not end pointers. That would be this. What you have allocated is n integers. And if you're on a 64-bit system, integers are going to be 4 bytes apart. But when you're writing this, when you're returning malloc to and assigning the result of malloc to these pointers, this is going to be 8 bytes. So you have to be careful about the size of whatever you're allocating. This is an example of overriding memory. So now you've allocated the right type, you have end pointers, but what you're doing is you're off by 1. Okay, so this is an off by 1 error where you are overriding memory, and C will not warn you. You do whatever you want. This is an example of not checking the size, and this is a stepping stone for buffer overflow attacks, which Alvin will teach you if you do software security. So if you have a 8 byte character array on the stack, and then you're calling getS, and the user can type anything, and then your stack pointer will point somewhere you don't know. And what they do is they make you do this. So in C library, there are these functions which do not check the size of the string, whether the string that the user has provided, the user of the function has provided, is big enough. And so the stack pointer, because it grows downward, the attackers can take the stack pointer where they want the stack pointer to be. So if the stack pointer keeps growing downward, it will eventually run into the heap. And this is a stepping stone for buffer overflow attack. This is a vulnerability. Misunderstanding pointer arithmetic. Here you're trying to add, trying to go to the next integer by adding to this pointer variable. So you don't understand pointer arithmetic. If you say plus equals 1, you go to the next integer. If it's the compiler is automatically going to, the compiler is smart enough to know that when you say plus equals 1 and the pointer is of type int, you need to increment by the size of the int. You don't have to explicitly say that in your code. If you have a pointer to a character and you say plus equals 1, the compiler is smart enough to know that you are trying to reference the next byte. So whatever pointer type it is, plus equals 1 will take you to the next variable of that type. Referencing a pointer instead of the object it points to. So here the programmer is trying to dereference size and then decrement it. What will actually happen is size will get decremented first. So you will have a new address and then you are dereferencing a bad pointer. This is where you need to understand your precedence, operator precedence. So that table, there's a slide in the table that shows. So size minus minus will be evaluated first. Size is a pointer. So you now have a pointer, or you now have an address to size minus minus. And then you are trying to dereference size minus minus, which is a problem. And so how do you fix this? You use proper precedence. You first dereference the pointer, get the size, and then do minus minus. And this is never return something on the stack. So here the function foo returns the stack is deallocated, but the last thing the function did, the last good thing the function did before returning, it returned a pointer to the stack, and the stack is deallocated. Stack pointer is somewhere here. This will be allocated to a different function, and then you basically have a pointer to something that who knows what it is. Never return a pointer to anything on the stack. Here we are very nasty. We are allocating something, we have a pointer, we free it, and then we free it again. Now you have insight into how memory allocators work. You are writing a memory allocator. Just do a thought experiment. What will your allocator do if you get 2 calls to free with the same address? So the allocator will free this, mark this block as free, and then when the user says free, give this block to someone else to serve a different request. And when the user says free X, what will happen? The allocator will free a block, and whatever the user's intention is, we don't know. Or this block might not have been allocated. Okay, and these are exactly the kind of errors we see in C programs, and these are exactly the kind of errors that managed languages with garbage collection try to prevent the programmers from worrying about. Here you free the pointer. At this point, X is a dangling pointer. It's not really pointing to anything. The programmer has freed the pointer, but now the programmer is using it again. Don't do that. Evil. You are using someone else's block to reference something. So once you free a block, don't use it. And all these errors, we see them in production software. Here, you allocate something using malloc and you never free. And this is a memory leak. This is a long-term killer. This is a memory leak. If the foo is called millions of times in a day, then your entire memory is full of this X, and the allocator doesn't know what to free because the programmer is not calling free. So here you are trying to free, you are creating a linked list. You're creating a linked list and you're freeing only the head. So head points here, you're only freeing the head, assuming that everything else will be taken care of by the allocator. No, the allocator is not that smart. You tell it to free head, it will only free head. You have to iterate and call free for each node in the linked list. There is a tool called Valgrind. GDB can only help you that much with these kind of errors. There's a tool called Valgrind that can do very powerful analysis. And what Valgrind does, it does binary instrumentation. It adds extra code in the text section of the virtual address space where your code resides. It adds extra checks, and each read and write it monitors, and then it reports to the user if there are bad pointers, overrides, references outside of the allocated block. And there are some other instructions for you to check for memory errors in your programs. Happy teaching break. I'll see you in 2 weeks. Right.
Sorry. So
Yeah.
this in lab 5, we use in that